Yeah, thank you for the introduction. My title of the presentation is Platinum Promoted Honeycomb Catalysts for Sulphuric Acid Manufacturing and Tail Gas Treatment in Complex Environments. It's the same product with two different applications. Now, I'm coming from P&P Industries. P&P Industries is a mid-sized company placed in Austria. Austria is here, Graz is here. The city of Graz is the location of our HQ. We also have subsidiaries in India, Germany, the Czech Republic, and Italy. So we have about 6 locations on 2 continents. We have under 200 employees, and the team of our company is quite heterogeneous, like it is necessary for a chemical engineering company. We have process engineering, mechanical engineering, electrical instrument engineering, hard and software solutions, as well as research and development, where I am head of, and also responsible for the catalyst division. Yeah, we offer on-site installations, startup training. We provide from the basic design until the detail engineering, and also EPC contractors for some special applications. Our history goes back to 2006, where P&P Industries AG was founded by Mr. Peter Gorichnik. He was our founder. Soon after, the laboratory in Stocking was our production site #1 was installed, and the company grew and grew, and we were first specialized in the so-called SOP process, which means sulfur oxidation process. We also have cooperations with metallurgical companies like First Alpine Kronblech in Austria, and in 2013 we successfully handed over our largest plant, which is able to make 504 metric tons of H2SO4 per day. Yeah, and then in 2015, the P&P Industries GmbH merges with the P&P Anlagentechnik. So our founder founded 2 companies, one more for chemical engineering and the other one more for automation. And these 2 were merged in 2015. In 2015 we also had our first SAR, spent acid regeneration double stage plant, started up. In 2016 we had a joint venture with Harbin Boao in China, which is a part of the Boshi company. And we had more and more cooperations. I don't go through everything. And in 2022, Mr. Herbert Ritter bought P&P Industries, so we had a turnover of who owned the company 1.5 years ago. So in P&P we have 3 different business units. Traditionally, we have the sulfuric acid and sulfur technology. We have waste gas treatment, which goes hand in hand with the first business unit, and precious metal catalysts, which are also placed into the first 2. Now, these compounds here, sulfur, H2S, CS2, H2SO4, H2SO3, SO2, are the chemicals which make our main business. We have 3 main plant types we offer. We have the spent acid regeneration unit. We have the sulfur oxidation plant, which oxidizes sulfur to SO2, and we have so-called SAC, which is a sulfuric acid concentration. We reach concentrations of about 93 to 98%, but oleum, which is super concentrated H2SO4, is also available. Furthermore, we offer solutions for volatile organic carbon oxidation in our thermal oxidation plants, or catalytic thermal oxidation. And we also offer DeNOx solutions for easier and complex environments. This is what we do. My topic today is the P&P catalyst portfolio, some case studies and applications. Maybe you saw our big slip outside. We use these ceramic honeycomb bricks for the following applications: for the oxidation of SO2 to SO3. I will later explain in my talk why this is a very important reaction. CO2 to CO to CO2 oxidation, which is important to detoxify flue gases, hydrocarbon oxidation, oxidation of sulfur-based species, H2S, CS2, COS. Maybe when you think about the production of fibers, CS2 is one component which is always in the flue gas and has to be oxidized and recovered. Chlorinated hydrocarbon oxidation, and the SCO, the selective catalytic oxidation of ammonia removal, is also part of our technology, and it all boils down to our platinum-based honeycomb catalysts with our proprietary recipes and applications. The advantages of using honeycomb catalysts in comparison to bulk catalysts. This slide I like a lot. So why should bulk catalyst be replaced by a honeycomb if this is possible? First, we have proven this technology in about 20 to 30 plants. We have very high turnover rates. For this topic, I show later a few graphs. When you compare the bulk catalyst to honeycomb catalyst, you have low pressure drop. You have very fast warm up of the material. You have usually a lower volume than with comparable bulk catalyst. You face not so much attrition. You have no screening. The reactor orientation can be standing up or horizontal. You have good shock and vibration properties. You have usually high geometric surface areas. You have no plugging due to no attrition. You have a very fine and defined flow pattern, so no channeling. You have usually no dust, most efficient utilization of precious metal, and it can be cleaned for a very long life. Once it is dirty, it is cost effective and has a lower toxicity. Now, why are we dealing with sulfuric acid in our company? Because I wrote it very boldly. Sulfuric acid is the most important mineral acid. This is due to the millions of metric tons which are produced every year. I just copied this graph. It is from 2015 to 2013. This is from a statistical web page. So from 2015, we had an increase from 250 million metric tons every year to 321 in 2030. So from the mineral acid, hydrochloric acid, nitric acid, H2SO4 is from the production volume here the most important. And as you can see from this graph here, the global sulfuric acid price trend, which was published on H2SO4 today, is very volatile. It also depends a lot on the sulfur price on the world market. So where is all the acid going, which is there produced? So nearly 50% is going to phosphoric acid production. Then there is this single superphosphate fertilizer production with 8%, ammonium sulfate fertilizer production 7%. So let's say half of all the acid production is used to feed the world, because without fertilizer, the production of these high amounts of food globally is not possible. Then we have 5% as a petroleum refining catalyst, for example, for the alkylation reactions. We have metallurgical application, copper ore leaching, pigment production, pulp and paper production, methyl methacrylate catalyst, nickel concentrate, and 20% are other applications. Now, how do we make sulfuric acid? One way, as I already said, is the sulfur oxidation. So we just burn sulfur. Where's my reaction? not there. So S plus O2 goes to SO2, and we recover the heat via heat exchanger, producing steam and electricity or heating energy. The second way is the sulfuric acid regeneration in our wet sulfuric acid process. So we burn the H2SO4 in a combustion chamber at about 1000 centigrades, generating SO2, H2O, and a little bit SO3. This is what we call the sulfuric acid regeneration. For example, once it goes through the alkylation process, gets a little bit contaminated by oils and everything, at the limit of about 83 to 86%, you have to regenerate it again. And then you have the concentration by distillation, and for energy reasons, we do this in so-called vacuum concentration units, or VCUs. Now, I'm done. Okay. Acid making general considerations. This is a block flow diagram how WSA spent acid regeneration plant would work. It first starts with oxidation. So we have our furnace, then we pull out the energy via this heat exchanger. We clean the gas via hot gas filtration so that the next heat exchanger will not be blocked. And also the catalysts are protected. Then in the first and the second converter, we oxidize SO2 to SO3. We also have a SCR catalyst on top of our oxidation catalyst. And what is necessary for acid making and SO3 generation are these interbed coolers, because the oxidation of SO2 is thermodynamically hindered at higher temperatures. So interbed cooling is necessary. And in the first and the second condenser, we bring our SO3 to the reaction with water, not with pure water, but with dilute acid, so that we can have no overheating of our vessel, but can recover a lot of the hydration energy by the heat exchanger. And the final polishing we make with the so-called LTCC, which is a low temperature carbon catalyst, to get nearly to 100% of SO3 or SO2 usage to H2SO4. Now, once we get a request from a client, this is from an actual request, how does it work? We have to consider the thermodynamic boundaries of our reaction system. So we know from our client data, we have about 11% SO2, 9% O2, the rest is nitrogen. Nice clients also give us the SO3 levels, which come from the combustion furnace. And then we have from the mass balance, the actual flows. Then we have some specification, what we want to have, classes 1 to 4. And then we calculate the thermodynamic equilibrium. And we have two main curves. The first curve is before acid making, because this is a so-called 3+1 H2SO4 plant. So we have 3 catalytic beds with interbed coolers, starting here at the top at about 380 centigrade, heat up, cool down, heat up, cool down, heat up. This is the third bed. Then we go to acid making. And the fourth one is this dashed line here. This is the equilibrium after acid making, which we have to consider during the design of this process. Now, traditional catalysis for acid making looks like this. You have your bulk catalyst. You have a steel frame, which is below these ceramic bricks. Then you pour it inside. Hopefully, you do it with more personal protection devices, because this is vanadium oxide, which is not so healthy. And yeah, then you have your reactor hurdles. And when you look at the toxicity of vanadium pentoxide, which is getting every year a little bit tighter, you have the H301 hazard sentence, which means it is toxic. It causes serious eye damage and so on and so on. And yeah, we thought about it and said, yeah, why not using platinum for that? Because platinum is not so toxic like the vanadium oxide. So our goal were catalysts with lower toxicity and higher efficiency. This was our goal in R&D. And yeah, then we did some measurements with our platinum catalyst. So we compared what you saw, the bulk catalyst, to our ceramic honeycombs with platinum promotion. And when we look at the activity pattern here, the red line turnover rate or yield versus temperature of a platinum catalyst. And if you compare it to a high-end vanadium catalyst and a standard vanadium catalyst, you see for the platinum you have an earlier ignition, which starts about here. And then the vanadium oxide, this is the first thing. The second thing, the yield, the turnover is much higher for the platinum than for the vanadium. And this is also written here in the second graph. It's the so-called space-time yield, which is defined that so and so many moles of SO2 react within an hour with 1 liter of the catalyst. So you also have a much higher space-time yield, lower ignition for the platinum than for the vanadium. And so we asked ourselves, why not do the reaction with catalysis of platinum? To be complete, I want to explain the ignition curve, which we saw here before at the slide. We have 3 or 4 regions. The first region where nothing happens at the left side of the temperature axis is kinetically controlled. Then ignition starts and we have a pore diffusion limitation. And the last one, the third one, is a gas phase transport. So usually for CO oxidation, this would be a flat line. And for the SO2 oxidation, which is thermodynamically hindered, you have this behavior. So over this ignition curve, we have here the SO2 equilibrium curve, which we got from simulation. Now, how is it looking in an actual plant design? I showed you on one slide the wet sulfuric acid. This is a converter for a DCDA, a double contact dry acid plant. They build it sometimes like this, or other times the pass 1 is at the bottom and it builds up. So you have your 4 passes, the interbed cooling, and final cooling, and sometimes there is interpass heating to heat the gas before the 4th pass. This is done to complete the reaction here at the 4th pass. Yeah, historic considerations. Many people would say, yeah, platinum is so expensive, and you are right, because with 25 to 35 gram per gram, it is one of the more expensive elements. But when we look in history, historic application, so platinum on asbestos used about 13% platinum at the catalyst. And when you look here at our actual platinum content, which I cannot disclose in absolute numbers because it's proprietary, you see that it is much, 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 much less. So the usage of the expensive material, has been improved. So what concerning the pressure drop, you also have much lower pressure drop when you consider the honeycomb in comparison to some 4 millimeter, 6 millimeter pellets, rings, or star rings. So overall, the higher reactivity also enhances a much lower bed height. So we don't need such high volumes of the catalyst compared to vanadium. So it is possible and allowed to build smaller reactors which have the same yield, which also leads us to the reduction of steel cost when we make a design. So we made this here now for carbon steel, 2 different grades, the 4301 and so on, several steels which we used. The reactor size can be lowered by a factor of 3 as a rule of the thumb when you change the catalyst system from vanadium to platinum. These were the things I already said. It is non-carcinogenic and non-toxic compared to vanadium pentoxide. You have higher turnover rates, lower SO2 emissions. For the overall reaction, we have a proven use in sulfuric acid manufacturing plants, and we had much much lower volumes. So this is a example for actual reactor design. We have our SCR hurdle, the platinum hurdle, the bed coolers, platinum heat exchanger. We have the possibility for one stage, which is not anymore done nowadays for the SO2 emissions. Usually we make two-stage design. You can have it round or rectangular design, depends on what the client requires. So the cylindrical beds will look like this. We have a comparison with the vanadium oxide bulk material, where you have at the outside the ceramic fiber compared with the catalyst bricks, which are insulated by this ceramic fiber in blocks of 4, I think, in this application. Yeah, these are now actual examples for installation. On the left-hand side, the vanadium beds, also with some pores there. This is one problem of the bulk catalyst, that there is sometimes channeling. So the contact time of the gas is varying. And on the right-hand side, you have now the installment of the platinum bricks, also with this insulating ceramic material. And these cylinders here are thermocouples, which are used to monitor the reaction temperature. This is also one possibility for a design when we fear to have a thermal runaway for high reaction rates. We install some inert brick in between the active material. Yeah, this is also a nice graph for traditional vanadium pentoxide catalyst application. This example comes for 5 passes, so it's a 3+2 plant. Now you have a frequency where you do the screening, so after 1 to 2 years you put out all this kind of organic toxic material, screen it, and put it back again. For the second one, 3 to 4 years period, and the third one 4 to 8, and the last 2 last about 10 years. So with ceramic with the ceramic honeycomb bricks, this cost is tremendously reduced. And now I have some chemical example. This is now a SEM, scanning electron micrograph of the wash code on the ceramic bricks. I call this the wash code and its working horses. This is the wash code, and the very small particles here, which have a diameter of about 25 nanometers, are the working horses where the reaction takes place. But the truth is that the particles are even smaller, like we saw today at this very good catalyst presentation we had earlier. These catalyst particles are much smaller. They are here. They have a diameter of a few nanometers, and this is the structure which lies below this. I call them the bigger platinum particles. So everything here, because the resolution of this instrument is reached, we went to a transmission electron microscope to get a better insight and characterization of our actual platinum on the wash code support. So, but where there is light, there is also darkness. This is now an example for arsenic poisoning. Sometimes when we get metallurgical H2SO4 after it is used, it is highly contaminated. For this example, we found arsenic. Arsenic was, this is the ADX signal of the instrument. It was sitting on the platinum. And then I went to my ICP OAS instrument, and we also found a bit arsenic, like 63 milligram per kg, which is a lot. And then we were asked, what can we do? Yeah, the arsenic poisoning also causes sulfur poisoning on the catalyst, because when the reaction heat does not heat up the catalyst anymore, sulfur can act as a poison on this material and stays on the surface, which makes the inactivation even faster. So I did some turnover tests to measure the yield, and this was the first This was the first measurement. We started at 380 and ended at 480 centigrades, and we got a very low turnover. I cannot publish here the absolute numbers. And after that, we heated it up, we cooled it down, we heated it up again. And when we look up to literature, we see that the arsenic trioxide goes to the gas phase at about 465. So the arsenic poisoning at this application was proven to be reversible. But it is hard to get the reactor up to 500 centigrades to desorb the arsenic. And then the arsenic will go out the stack, and it's also not so nice. So this is not a solution on a plant scale. What else do we have? Yeah, sulfur poisoning. As I said, first we have a reaction furnace where we decompose the H2SO4 to SO2. But very important is the residence time in the furnace, and that the droplets of the acid are very, very small, because H2SO4 has a very bad decomposition kinetics. And if the acid nozzles are not spraying so well because they get corroded, then we have H2SO4 and SO3 at the catalyst. Maybe everything is cool. The dew point of the material goes in a bad direction, and then we have sulfates forming at the catalytic layer. This was the case for this sample. I did some STA, which means simultaneous thermal analysis. Heat everything up until 800, 900 centigrade. And monitor, the blue line is the SO2 emission line, the SO2 emission. So regeneration of this catalyst is possible once it is over 650 centigrade, but this is also not possible at the plant size. This is also another example for for poisoning of the catalyst in the sulfuric acid application and the reversibility. Now, the final example of my presentation is the CO abatement in complex environment. This was basic design. It was a hot gas filter. The hot gas filter should provide a dust-free atmosphere for the catalytic reaction here. We know from literature that the oxidation of CO to CO2 starts at 200 centigrade over platinum honeycomb. But the client said there were few traces of SO2 and a bit of dust there, so there will be no problem, right? And what happened, we measured the actual reaction, the CO2 oxidation at our test rig. The ignition is even lower. This is a graph for two different hourly space velocities. Yeah, and then everybody was happy. We started up the plant, and the first batch of catalyst lasted 6 months, the second one 1 month, the third batch 8 days, the fourth batch 2 days, and the catalyst itself died very fast. And the turnover of CO was also measured again, and we see here a shift of ignition. And then the question came to me, what happened? And then I know I'm a little bit running out of time. We see here now a degradation of the wash coat layer. We see here the growing of our platinum particles, because remember, we started with 20, now we are at 101. We also had arsenic, lead, phosphorus, and a little bit of thallium. So the gas phase was very toxic. So we could not reach the CO limit. We put the catalyst to the hot gas filter to increase the reaction temperature, which enhanced the standing time of the catalyst up to now 6 months in operation, and increased the lifetime a little bit, because many of these toxic reactions are not favored at higher temperature. So, okay, now to give an outlook, detailed studies of catalyst applications in the field of acid making and CO abatement were presented. The optimization of the catalyst recipes goes hand in hand with process design. So I'm very close to our process engineering department in the company. The development of new catalysts must be monitored from bench scale to lab scale, and yeah, catalyst development and monitoring never stops. Thank you for your kind attention.